Hi, this is Nastanowski, and we're continuing on our tour of monoidal category theory, and we're going through every single section of this book. Okay, we're up to section 5.5, which is about string diagrams. Now, string diagrams is a way of displaying different aspects of monoidal categories. Okay, and it's pretty. Okay, literally pretty. And the reason is because rather than dealing with a lot of different diagrams or equations, you can actually make pictures of these things. And we do, and we will for the rest of the book. Okay, and it's used through, string diagrams are used throughout the literature very much. Okay, very, very much. Okay, and there are entire books written just from the string perspective, string diagram perspective, and they make things nice to do. Okay, with our book, we use diagrams and we use string diagrams. We're not solely string diagrams. And I just, there's a great line from my thesis advisor, Alex Heller, and he used to say, he said, one good sentence is worth 1,000 pictures. Okay, in other words, he always liked to have things clearly expressed. Okay, anyways, so we start off talking about string diagrams. There's going to be a lot more. The reason why I'm hesitant about string diagrams is because it's conventional. It's not, we're not talking about truth here. We're talking about how to represent things. And every different author can come up with their own ways of representing things. And there are certain things that there is a consensus amongst the literature, but we don't only do string diagrams. Okay, that takes care of that. Okay, just in terms of the convention, it's not even clear how to make string diagrams. In other words, what direction do you do? In other words, do you have your string diagrams going this way? Physicists like to have their string diagrams going like that because they're talking about something like Feynman diagrams. Okay, you have things like that, and basically time is always going up. So in some sense, their diagrams are going up. Lots of mathematicians have their things going down, their pictures going down. So again, it's conventional, and you can argue about it because, you know, you explain something one way and the other people explain something the other way. Okay? We're going to try to go mostly this way in our string diagrams. And again, this is just the beginning of it. Okay, so let's get busy. The main idea is as follows. Usually, you have an object, you have another object in a category. The morphisms represent a way of changing one object into the other object. Okay, that's classical category theory, and that's very good. Okay, and we will use this. Okay, but string diagrams does something very much different. What they do is, instead of having this diagram, they're going to have, so we might call this F. They're going to have this diagram like this. Okay, and the way to think of this is some type of process or wire going in, and you're doing something to the wire, you're doing something to the contents or the input, and this is the output. Okay, so this is the input, this is the output, this is an object, and it goes through a process and goes that. Okay, so there's some type of duality here. Here, the objects are dots, and the line is a process. Here, the line is the objects, okay, and a shape or a dot or something stopping it is the process. So you might write this like this. Okay. I just want to say something just, not really to do with monoidal categories, but to do with physics, namely Feynman diagrams. Again, we have time going this way, we have space going this way, Okay. Here, okay, the objects, I'm sorry, the lines are again the particles. So a particle is going like this. Okay. Okay. And then one particle meets another particle and something happens. They change. Well, the dots are the changing, the processes that changing. The single particle moving from one to the other, that's not really changing anything. So in some sense, Feynman diagrams are like this, not like categories. Okay? Again, you want to think of this as a particle, you want to think of this as a particle, and you want to think of this as a particle, and here they're getting together and they're interacting somehow and they're coming out different. And here they're in, so the processes are at the vertices like this. Okay, so it's not a strange thing, but you have to keep this, you need both. To understand it, you need both of these different ways of dealing with this. And that's very interesting that these dual notions somehow both work. Great, okay. Sometimes we're interested in showing the direction of this, so we put it like that. Okay, sometimes without the directions, and sometimes the direction is inverted. So for example, we could go this way. Okay, here's B, here's A, and we have sometimes like this. Okay, we saw something like this in terms of vector spaces. So we can have a vector space V and a linear transformation, and it turns into a vector space W. Okay, let's just put the arrows here. But then we can talk about V star, T star, W star. Okay, and the point is those arrows go the other way. Okay, so we have to keep track, sometimes we have to keep track of which way these arrows go. Very nice. Okay, let's keep it simple, not worry about that. Main point, oops, you can have an F process that takes A's to B's, but then you can have a G process which takes B's to C's. Okay, and that's very nice. You might call this sequential processing. You might call this sequential processing. So that's doing two things at a time. And again, sometimes we might want to put in arrows here to show the direction that they go. Okay. Okay. And again, sometimes people draw these things going up, and sometimes people draw these things going down. Here's F, and then here's G. Again, there's no wrong or right. These are just different ways of presenting things. When you're presenting mathematics, there's one way of doing it. When you're presenting how to display mathematics, there's many ways of doing it. Okay, great. Now, let's say we have, so that would correspond to F composed G. That's very good. Okay, let's say you have a function, instead of from A tends to B, it's something like this. Instead of from A to B, it's A tensor B tensor C, and it goes to X tensor Y. Okay, this is an object in a category, this is an object in a category, this is a morphism from one object to the other. We might write it like this. Very nice. But how would we write it in terms of string diagrams? And the way we would do it is as follows. A, B, C, X, Y, F. Okay, so again, F is a process that takes A, B, C's to X and Y's. Okay, so this is a nice way of describing it. Okay, and again, we could have other processes that we have some of the things coming there and going there. So we're going to connect up all these different string diagrams. Okay, hold on. Okay, we might have something like this. F, you know what, I'm always going to put the F on top of the arrow. So we might have something like this. The identity goes to A tensor X tensor Z. Something like that. Well, in that case, the way we would write it is the identity, that's the unit of the monoidal category. Oops, sorry. It's not from that. The line becomes that. And here you have F, and here you have A, X, and Y, and Z. Okay, so that's a nice way of doing that. But we many times shorten that. And we shorten that to leave the identity out. Leave the unit of the monoidal structure out. So you have nothing going in and you have things coming out. Okay, and of course you can go the other way too. So for example, I don't want to draw it like that. And for example, you can have G here, and you can have 4 different things here, W, X, Y, Z, and it can go to the unit, and we'll leave that alone. Okay, what's more interesting is well, what happens when you come from the unit and you go to the unit. So we have a map here, and you come from the unit and you go to the unit. Okay, great. Now, if you have 2 of them, you can compose them. Very nice. But what did we say about leaving out the identities, leaving out the units? So you can compose them like this. And this would be composing them. Okay. We'll see this in a second. In 3 minutes, we'll see this more. Okay, so again, if you have X tensor Y, and you have a function F to the identity, the way you can write this is, here's X, here's Y, and it's not going anywhere. Okay, and again, convention leads a lot of different ways, but some authors write this like this. This is X and this is Y. Okay, and of course you can have the other way around. I going to X tensor Y, that's going to correspond to starting off as nothing. Okay, well, so let's write the box. And then X and Y come out, which again can be done like this. X and Y. Okay, and you're going to see later on, we actually sometimes do follow the up-down way of talking about it. And so then this would be X and Y, and this would be X and Y, or the other way around. Okay, so like I said, there's many different conventions for displaying mathematics. Okay, great. We're not only interested in one operation, sometimes we're interested in 2 operations. So, for example, we can have A to B, that's one operation, and you can have C to D, that's another operation, and the way we'll describe them in string diagrams is A, F, B, and C, G, D, okay? And this leads to another way of composing morphisms, not only sequential, but parallel. Okay, so we're going to have that. Okay, and this interchange law that we mentioned a few times is a discussion about this. So let me just use the same thing I use in the book. F, F prime, G, G prime. Okay. And we talked about this a few times, and it's very important. Question, is this, close this off, F parallel, sequential with F prime, and G sequential with G prime, and you're doing this sequential operation in parallel with this sequential operation. So you might draw this like this. These two are important. These two are important. And you're doing one parallel thing, one operation parallel with another. Or draw the same thing, okay, and say like this. Here's your F. Here's your F prime, here's your G, here's your G prime, okay? Or maybe you should say, no, close this off. Here you have a parallel process, F and G. Here you have another parallel process. And what you're doing is you're doing this parallel process followed by this parallel process. Main point. Doesn't matter if you look at it this way or this way, they're equal. And that's exactly what the interchange law talks about. Okay, so that's very nice. It's a pretty way of seeing it. Okay, that's a pretty way of seeing it. Okay, great. I just want to go through a few other. Now that we have these diagrams, I want to go through some interesting 3 or 4 other ways of looking at stuff that we looked at. For example, if we have adjoint functors and we have a functor from the category B, a right functor from the category B to the category A, okay, the triangle identities for a junction come out to be something like this, that this should be equal to, oops, here's category B, here's the unit, okay, so that's eta, that's epsilon, and that's category A. So that's one of the string that's one of the triangle identities, okay? So B tensor, that's a way of looking at one of the triangle identities for an adjunction. So the right morphism is equal to that. We drew this as, I don't know, something like this. B equals okay, anyways, you can look it up. Okay, and of course there's another one for the left. Okay, main point, the units and co-units, they go from identity to LR or RL. Okay, so again, there's another one like that. Great, let's talk about the Ekman-Hilton thing. Remember what the Ekman-Hilton thing says, okay? The Ekman-Hilton argument. What it says is, take the unit of a monoidal category. Well, harm from it, if you look at endomorphisms, not orthomorphisms. Orthomorphisms are isomorphisms. Endomorphisms are just morphisms. If you look at morphisms from there to there, it forms a monoid. Okay? In any category, it forms a monoid. So if you look at all these different things, they form a monoid. Okay? However, if you look at the category as a monoid, so you have a monoid as a monoidal category, then the endomorphisms not only become a monoid, but they become a commutative monoid. Okay, now morphisms from here to here are just written as boxes. So if this is F, this is the box. If this is G, this is the box. Okay, but there's no reason why I should draw it underneath. You might want to draw it one after the other, because you can compose them this way or this way. So this F can be composed with G, or G can be composed with F. There's no order in which they do it. Okay, fine. Okay, but there's another thing you can do, namely, you can also have AI tensor I and I tensor I, okay, and you can compose them F tensor G, okay, which would look like this. So you can compose them sequentially or parallelly, okay? There's a little bit, again, in that proof that this monoid is commutative, you have to talk about this. So this is a morphism from here to there, from I to I. So even F tensor G can also be looked as a morphism from I to I. Okay, great. So now, in the book, I have lots of diagrams like this. Again, thinking of these morphisms from the unit to the unit as just simply boxes, so you can draw the box like this, F and G, and then you can draw the same, this is the same thing as F and G, which is the same thing as F and G, which is the same thing as G and F, okay, which means it doesn't matter how you compose them, okay. This says sequential processes are, these two, the fact that these two are equal says sequential processes are commutative. The fact that these two are equal says parallel processes are commutative. Okay, nice. Okay, so again, what we're doing now is, now that we have string diagrams, let's go back and look through some of these more interesting things that we saw. Okay, great. How do I do this? A, B, C. Okay, consider this. A, B, C, where B and C are very close. Now consider this. A, B, and C, where A and B are very close. So you might write this as follows. A goes to A, C goes to C. B was close to A, but B was close to C, but now gets close to A. Okay, and the way to envision this is A tensor B tensor C. And this is A tensor B, they're close, tensor C. Okay, so now we're talking about associations. Very nice. And the section closes with a nice way of looking at the pentagon condition. I don't want to do it. I don't want to draw it because it's a little bit, you have to be careful the way you draw it. But there are different ways of doing this. So this is the top of the pentagon. This is the bottom of the pentagon. You have 1, 2, 3. This is the top, 1, 2, 3, 4. Okay, these, so that's where you get it. And what you're simply doing is you're showing what's close and what's far. And by the way, there's physics ways of looking at this. In other words, think of this as two particles that are very close, so close that you can think of them as connected. Okay, and then you have a third particle that's far away. What happens if one comes close to that? And physicists actually talk about such things. Okay, so again, this is just the beginning of string diagrams. We're going to have a lot more string diagrams as we go along. Okay, but more importantly, the string diagrams get more and more complicated. Okay, because we're going to put on more bells and whistles onto our diagrams. Not only are we going to have squares, but we're going to have other types of things. And again, as much as I do string diagrams, other people do string diagrams much more, and they take it much more seriously and do everything like that. We're going to have braids. We're going to talk about braids. We're going to talk about thick braids. We're going to call them ribbons and stuff like that. We're going to have lots of pictures to do this, and it's a very nice, helpful way of doing it. Okay, have a wonderful day.